So let's look at this limit of the Riemann sum. So before we had in section 5.1 all our intervals were of uniform length. Every one of them was of length delta x. They were all the same. That doesn't have to be the case. We're not going to look at any problems where it's not the case, but it doesn't have to be the case. You can have a bunch of different length intervals. As long as the largest one is going, the length of it's going to 0, because n's going to infinity, then you're going to get the same value no matter what when you take the integral. So since in this definition we had the little x sub k squiggly, meaning that's my sample value from each interval, it doesn't matter what that value is, and it doesn't matter how big the interval is. So since it all goes to the same limit, we may as well just make life easy and use the right endpoints. So let's look at an example to make things sink in a little bit. So here we're asked to express this as a definite integral. So this is defined on the interval 2 to 7. So remember what we're doing with this. We're subdividing this interval 2 to 7 into n subintervals, and we're going to take a value from each subinterval that we're called x sub I squiggly, and we're going to evaluate a function f at each of these values. So if I look at this expression, I can see this is how I get my function f. So it's 5x cubed minus 4x. The delta x is analogous to the dx, represented by the dx in my definite integral. And then 2 and 7 are my limits of integration. So I can rewrite this as this definite integral. So we had the word integrable in the previous definition, and a function's just integrable if this definite integral exists, if that limit exists. So this is just kind of reiterating what we talked about before. The definite integral can just be defined as the limit as n goes to infinity of the right-hand Riemann sums, because it doesn't matter, again, what x value you use from each sample, from each interval, so you may as well just use the right endpoints because that makes life easy. And so that's x sub k is just a plus k times delta x. So again, if you want to estimate the definite integral, you use just the Riemann sum without the limit. But if you want to evaluate the definite integral, you have to take the limit of that Riemann sum. Again, area, these are not symmetrical. These portions are not equal. So the net area is minus 0.48. Here's another example, the same graph, but this time we're going to look at the left endpoint Riemann sum. So again, same intervals, same delta x, but this time we're just going to evaluate the function g at the left endpoints of the intervals. So I have g of 2, g of 14/5, which is 2 and 4/5, g of 18/5, etc. I sum these, multiply by delta x, and I get that same value I got before with the right endpoints. And that's because g of 2 in this case just happens to be equal to the rightmost endpoint, g of 6. So that's why they're the same. Finally, we'll look at this example with the midpoints. So those are, again, same intervals. This time, instead of picking the left or the right endpoint, we're going to take the midpoint. So we take the midpoint of each interval. So the first sample value would be the midpoint of 2 and 2 and 4/5, which is 12/5. The midpoint of this interval is 16/5, etc. We do the same thing, except this time we're evaluating g at these midpoints. And we sum them, multiply by delta x, and we get minus 0.64. So that's a little better estimate than R5 or L5 were, because the actual value of this definite integral, which we'll see how to do later, is this value. So in general, if you're approximating a definite integral with a Riemann sum, the midpoint rule is the best for approximations. A little note about notation. The text uses x bar, a bar above x values, to denote the mean. With what I'm using, I can't do that. So I'm using x sub m sub k. Again, this is just an approximation. When we find the definite integral, we're finding the exact value. Here's another example. We're going to look at comparing two problems, once by estimation with Riemann sum and once by actually finding the definite integral. So this problem says to use the midpoint rule with n equals 5 to approximate the integral. And now this time I do have the function. It's x squared minus 4x plus 2. So we're going to have 5 subintervals, and our interval is 0 to 1. So delta x is 1/5. So a is 0. So we're going to add increments of delta x. These are our intervals. So taking the midpoint of each interval. So this means that the estimate of the definite integral of 0 to 1 of this function is going to be the sum of evaluating this function at each of these midpoints and then multiplying by delta x. And I had to continue this on another line. This is just one sum. And summing that up, you get 0.33. So that's an estimate to the definite integral, to this definite integral.